I'm Steve Goldman. I'm a postdoctoral fellow at the Space Telescope Science Institute in Baltimore, Maryland. And today I wanted to talk about the work that we've been doing in M31. This work marks the first real census of the evolved stellar population in a metal-rich galaxy, and also the first calculation of the dust budget in a metal-rich galaxy. So the data that we've been using is the data from FAT. FAT surveyed around a third of M31's disk and resolved around 120 million stars. We have photometry in 6 bands with FAT, and we've supplemented that with data from Spitzer from 3 to 24 microns. So with this data, we've identified all the relatively dust-free AGB candidates with FAT, and the dustiest AGB candidates that are obscured in the near-infrared and optical, we've identified those with Spitzer. So here I'm showing all of our TP-AGB candidates. In total, we have around 370,000 TP-AGB candidates and around 5,000 extremely dusty AGB stars that we expect are in their superwind phase and that we expect are producing the bulk of the dust in M31. In addition to these TP-AGB candidates, AGB stars have already been identified in M31 in smaller regions across the FAT footprint. For these stars, the chemical composition has also already been classified as oxygen-rich or carbon-rich. So in total, there's around 20,000 oxygen-rich AGB stars and around 350 carbon stars. And of these, we have identified those that are significantly dusty. And then in addition to that, clusters have been identified in M31. Here I'm showing all of the clusters that we've identified AGB candidates within. So for the younger clusters, we expect that these AGB stars are probably not within these clusters because these clusters are relatively young and too young to probably host an AGB population. But for the older clusters, we have the age, the mass, and for many of them, the spectroscopically measured metallicities. And so with this large data set, we can finally calibrate a number of things, from mass loss rates to dust production rates to the boundaries of carbon and oxygen-rich chemistry. So in the past, this is a figure from Martha Boyer's 2013 work showing the parsec models and the boundaries of oxygen-rich chemistry, shown in blue, and carbon-rich chemistry, shown in red. Now, a lot of models conflict on these boundaries, and they're very uncertain. And it's still unclear if there's a ceiling in metallicity for carbon star formation, whether you can create a carbon star in a metal-rich environment. And these previous models, as well as many other models, are calibrated using 30-year-old cluster data from the Magellanic Clouds. And it's been found that these clusters are compromised as calibrators due to an effect named TP-AGB boosting. And this is related to the unique star formation histories of the Magellanic Clouds. And so now, with M31 cluster AGB candidates, we finally have pockets where we can determine the chemical types and confirm the boundaries of chemistry. This is especially exciting with the launch of James Webb later this year. One of the other things I wanted to bring your attention to is the carbon star luminosity function in M31. Here I'm showing the Spitzer data from the Magellanic Clouds, from the SAGE survey, as well as our carbon star Spitzer data, and the rest of the Spitzer data in M31 is shown here in gray. And what we're seeing here is a much more narrow range in the luminosity function for the M31 carbon stars. And this is what we're expecting, as we expect that the efficiency of third redshift events decreases in metal-rich environments. And while we're complete for the brightest stars, we lack the sensitivity on the fainter ends. So we need some more observations to confirm this, but it's suggestive of a more narrow progenitor mass range for carbon stars in metal-rich environments. So there's a lot of stuff that we can do with this new data set, which is large and similar to those of the Magellanic Clouds with the SAGE surveys. We can finally constrain the effects of metallicity on mass loss, on dust production, and fine-tune those mass boundaries for the carbon and oxygen-rich chemistry. So thank you for listening to the talk. I also wanted to mention another talk that I've given on the symbiotic Meyer system, HM Sagittae. So thank you.